Okay, cool. So let's get started with today's lab. I'm going to be checking all these boxes. Let me tell you what all of these funny things actually mean. So on the right hand side, you have forces, yeah, the sum of forces. There are a couple of things that I checked. We'll see in just some time. I'm going to take off sound because it doesn't make sense. You'll hear weird noises, so we don't need that. As you can see, this is, well, a tug of war. So initially, before we start everything off, we expect you to click on reset all. I'm not going to do that the first time around. As you can see, there's nothing there, so it says the sum of forces is 0. Is this okay? Is the setup fine? What I can do is I'm going to add guys on the left and the right hand side, and then we'll see which direction this thing moves. Okay, that's the idea behind this. Cool. All right, hold on. Okay, great. So let's initially, to start off with, the card is obviously at rest. Yeah, there's no green, I'm sorry, not green, there are no blue guys nor any red guys on either side of the card. And so what we're going to do is we're going to add one small red guy, any of the points. I'm just going to put it here. So immediately you see that there's a go button that's come. Where do we chat? We're chatting right there, Jacob. Where you're chatting right now. Yeah, that's the correct chat window. Good to see that you joined us as well. Okay, you can see immediately that there's a green thing that says sum of forces, which is, well, obviously the sum of all the forces. Since there's only one force right now, which is the rightward force, that's also showed by this 50 Newton in red. Do you guys see that? Everyone's able to view this, and you guys know what I'm talking about? Okay, great. Now let's click on this go button. Obviously, it's simply going to move to the right, yeah? Move slowly, and yeah, this goes on, and this was what is expected. Yeah, I'm just going to pause this. I'm going to reset everything. Obviously, there's an external unbalanced force. There's nothing else balanced in the dude to the right, hence it should move. This is very straightforward. Yeah, nothing much to understand. I'm just going to click on reset all now. I'm going to check the check boxes that say sum of forces and values again, so it's back to the initial starting point. Now what I'm going to do is I'm going to put a big guy. I haven't changed the mass of the card. I haven't changed anything else. What happens now? Let me add a couple of more guys, yeah, so that you can actually see the difference. Now you see that the sum of forces is 200 newtons, and they're all of the forces towards the right, yeah, because there are guys only on the right hand side. Clear? Nothing really extraordinary happening here. I'm just increasing the magnitude of the force, right? So what do you think is going to happen now? Do you think that the cart will move faster, slower? Yeah, it'll move faster. It's common sense. Exactly. More guys pulling the cart, it should move faster. Let's see if that happens. Yeah, seems like it. Yes, it seems like it's going. Red already won, so we don't have more space. Yeah, faster. Makes sense. Cool. So obviously the magnitude of the force matters on how fast a body moves. You guys already know this in the form of equation. I'm actually showing this in this lab that it makes sense physically as well. Again, I'm going to click on reset all now. I'm going to check both these boxes. And now what I will do is I will put one medium guy. Medium is this guy, yeah? This guy in the middle. This guy is the medium guy, the red guy. I drag him and I put him here. And I take another guy on the right hand side. What does this mean? It doesn't matter. By the way, let me make one point clear. It doesn't matter at what point this guy is standing. Yeah? If I put it at the first point or the second point, right now, like the red guy is on the second point and the blue guy is on the first point, first knot of the rope. Let's assume that that doesn't make any difference. It wouldn't. In this case, it wouldn't. Yeah, it's just moving in one line. So what do you see? What is the sum of forces? It says 0. Does that make sense to you guys? Are you comfortable with the fact that the sum of forces is 0? They are the same guy, the exact same forces being applied on both sides. Okay. So now when I click go, what do you think is going to happen? Yep, makes sense. Yeah, and it doesn't move. I can keep this thing running for as long as I want. It's not going to move. Those guys look like they're putting in a lot of effort. They are, but nothing happens. Exactly as all of you guys have correctly said. So the forces, there are two things that must happen. One is that the forces have to be unbalanced for the body to move. And what we discovered earlier is that the forces have to be external forces. External, internal, you guys have some sort of an idea already. And in this setup, it's clear that this is an external force. Yeah, I'm pulling it with the rope, and the rope is outside the body, obviously. Okay, let's change this tab to the next cool simulation. Are you guys okay with this? Everything discussed so far? Yes? Okay, great. There's a guy next to a skateboard. We assume that there's no friction, okay? In this lab, again, we assume that there's no friction whatsoever. Again, I'm just going to be checking all the boxes, and there's a speedometer, yeah, over here in the middle. Notice that, remember, a speedometer only cares about how fast you're going. It does not care about your velocity. It doesn't give you direction. So velocity of +5 or -5 is going to be the same on the speedometer. It's just going to show you the absolute value. Are you guys comfortable with that idea? Does that make sense? It's extremely important. Like in your car, when you turn the car around, it doesn't show you direction. Yeah, that's a simple idea. Okay, now I'm going to click on the pause button. What happens now is that basically the simulation is paused. I'm going to add some mass on this skateboard. So I'm putting it on a fridge, and immediately you see another rider over here, which means that I can apply a force. Now that there's a mass, I can apply a force to it, yeah, either to the left or to the right. That's what this direction means. You guys are okay with this thing? The -500 meaning towards the left, and the +500 meaning towards the right, depending on which way I move the slider. I'm going to set the force to be around 50 newtons, yeah, exactly 50 newtons. Now, as soon as I press enter, you can see that the same direction thing comes. Yeah, this guy is pushing towards the right. He has a tendency to push. Right now the simulation is paused, so he's not actually pushing. But if I press play, he is going to push it towards the right. Is that okay? Yeah? Okay, so speed is 0. Everything is stationary. Now it's obvious, just like the last experiment, once we start this experiment, the mass should start moving toward the right. But will it be uniform motion or non-uniform motion? Which one do you think? Any ideas? Okay, one of you guys saying non-uniform. What do the rest of you think? Okay, some of you think it's uniform. Let's see. What we're going to do is we're going to hit the play button. We're going to hit the play button, okay? And once we hit the play button, that's very complicated, Ashna. I'll tell you. Wait, hold on. Let's just take it one step at a time. Once I press play, if the speed changes, then it is non-uniform motion. If the speed remains constant, it is uniform motion. Are you guys comfortable with that idea? That's pretty straightforward, right? Let's not worry about how it would actually behave. Let's first decide what uniform and non-uniform motion is, just to be clear again. Okay, all right, now that that's out of the way, I'm going to hit the play button. What happened? Slowly and steadily, the speed keeps on increasing, right? Clearly, the external unbalanced force produces acceleration. And obviously, acceleration is in the direction of the net external force. Yes? Agree? You're seeing it, so you have to agree. Yes? Now, you also see that it is not uniform motion. You guys have done a lot of equations, but practically, this is what makes sense. Yeah? Notice I'm not saying, I knew one of you would ask me that question. How is only 50 newtons moving in 200 kilos? The point is, don't worry about the thing is there's no friction, right? So any amount of force will actually move the body. Only if there is friction. Yeah, exactly, Arjun. The acceleration is the value that you've mentioned there. And Arjun Nair, how only a 50 Newton force? Do you guys understand this? Any external force will move a body. Why we don't see this in real life is because there is friction in real life. We have assumed that there is no friction. It was excellent point that you brought up there. You cannot see this in real life, yeah? You have to apply some amount of force, and 50 Newton seems like a small force. But in this case, it will, any amount of force, even a force of 1 Newton will move the body. It will move the body slowly, but it will move the body because, well, there's no friction. Make sense? Yes? Okay, great. Let's reset everything. And again, click on the check boxes that I want. I'm going to reduce the mass now to say 50 kilos. And yeah, set the same speed, the same acceleration. Before I do that, remember I have to again pause the simulation, otherwise it will start off and we won't have time to discuss. So I'm going to pause this first. And as soon as I do that, you can see that the same magnitude force is there, it's the same direction. So what's going to happen? Obviously it's going to move faster, right? Is that intuitive? Do you guys follow that? Yeah, okay, makes sense. Yeah. Let's look at the speedometer. You can see that it moves faster. Yeah, the speed at which the red bar is moving ahead is a lot faster. Yeah, pretty simple stuff. Okay, let's pause this experiment without changing anything. Notice what I'm going to do. I'm going to set the force to 0. I have paused this simulation, but when I replay this, what do you think is going to happen? And I hit enter. 0 force means, well, the robot stops pushing the box. What does this mean now? Notice that the speed is still the old speed when the experiment was paused. That was the point of pausing the experiment. Okay, one of you seems to have some sort of an idea. Some confusion. Ashna says same velocity. Arjun says no movement. Arjun Nair says there is no friction. Won't it keep going? Yeah. Let's see. Let's see. You guys have some conflicting ideas. That's good. It gives us room for improvement. Let's see what happens. See the speedometer. It doesn't change. Right? This is what makes sense. This is nothing but the Newton's first law, right, of inertia. Unless acted upon by an external force, a body will continue to be in its state of motion or rest. Right? Make sense? Since there's no friction, as Arjun Nair correctly pointed out. Everyone clear on these ideas? Extremely important stuff. I'm going a little slowly because this is very important. Okay, great. Now, why did this happen? Because the robot stopped pushing the cart. So, no external unbalanced force acts. So, the speed control basically remains the same. As you can see, from the time we started this discussion, it's been at the exact same point. Well, this makes sense from Newton's first law, as I just explained. Now, let's pause this and do something cool. Now I'm going to put a negative 50 Newton force on this. So robot is back into the picture. He is applying a force in the opposite direction and the magnitude is 50 newtons. Okay? That's what negative 50 means. Yeah, towards the left, and that arrow shows that it's towards the left. That makes sense. Clear? Okay. Cool. So what I'm going to do now, what do you think is going to happen? First tell me, what do you guys think is going to happen if I press play again? You guys seem to have figured it out. Okay, let's see what happens. Let's see what happens. You guys have some sort of an idea? Let's actually push play button. Some of you are saying that it becomes 0 and accelerates again, and it slows down and goes in the opposite direction, or one of you says that it's going to move left. But aren't we talking about speed? Yes, we are talking about speed. I'm not talking about anything. I'm just asking you guys what is going to happen. Don't worry about speed or velocity at this point. I'm not asking about that. Right, I'm just asking you guys what happens at this point when I push this. Yeah, to the box. What happens to the box? Jacob, do you still think it's going to move to the left immediately after we explain that? Let's see. Let's see. Don't worry about it. You can see that it slows down first. You see that speedometer? It seems to be braking. Yeah? Reaches and then back up. Yes? Does this make sense? Is this okay, guys? Or is this getting a bit confusing? Cool? Everyone's cool with this? Right? Remember This is exactly like the motion lab. I'm going to pause this simulation. Remember the motion lab, one of the last cases we did was that the velocity and acceleration were in the opposite direction. So if we had a positive velocity, you had a negative acceleration. That's exactly what's happening here. Yeah? So at some point it's going at some speed, and then it slows down, and then it goes back up. Correct? So the leftward force is constantly accelerating towards the left. And what you see is that, well, the body actually slows down towards the right and then moves back towards the left. Does this make sense to everybody? Okay, I'm just going to pause this simulation for a minute. Yeah? And just go back to the class window. I'm going to pause it now, okay? Okay, cool. So we've just seen that it's possible to relate the ideas we saw here back into the equation form, simple equation. Yeah, just v equal to u plus at. That's what we saw. And we rationalized that, okay, this makes sense using the equation as well. Now, let us also consider friction. Let's go to the next tab. I'm just going to reset everything here. This one's also reset. Okay, cool. Yeah, the same stuff. The only extra thing that's happening here, as you can see, is there's a slider for friction. Everyone sees that? The mouse pointer's on that right now, yeah? There's a friction and the slider's right in the middle. I'm going to move it all the way to the left. I'm going to pause this. So notice what happened at the bottom, yeah? This looks like it's ice. If I make it lots of friction, you see it's got a weird texture. So basically no friction, ice, yeah, kind of makes sense intuitively. Now, I'm going to put a 50 kilo mass in front of our good friend. You see the same slider here for the force. I'm going to put in a force of 50 Newton. Now, what do you think is going to happen? Is this going to be similar to what we've seen, or is it going to be different? What do you guys think? No, it's not possible to have no friction anywhere. Yeah? There are some pretty cool research things that are going on to try and get zero friction, but it's practically not possible. It's like 0 Kelvin, or temperature of 0 Kelvin. It's like a theoretical concept. But we do this so that it makes life easier for you initially to learn these ideas, to understand these laws. And once you guys follow the basic ideas, then we go ahead and say, hey, you know what? Real life does have friction. Let's try and analyze that next. That's what we're going to do. Okay, so you guys see the same thing. I mean, you guys seem to agree that it's going to be the same thing towards the right, exactly same as the last thing. Jacob, it will not move right faster. I know it looks like he's on ice, so he should move faster than earlier. But basically, in the last tab, we had no friction, and that's the same thing that's the exact same scenario I'm rebuilding in this case. So when I hit play, it's going to have a similar thing. Yeah, the speed is moving at the exact same thing. You can actually check if you have side-by-side windows and run them. You will see that the speed runs exactly. It increases at the exact same rate. As one of your friends pointed out, was something like 0.25. Oh no, not 0.25. In this case, it's 1 meter per second square, since it's a mass of 50 kilos. Okay, so it's exactly the same. This makes sense because there's no friction. Now I'm just going to pause and note the speed. Yeah, it's somewhere in the middle. Let's put the force control to 0. What do you think is going to happen now? Guys? What happens when I press play? Keeps going. What happens to the speed? Does it increase, decrease, remain the same? There's only 3 things that can happen. You can't have none of these options over here. Constant velocity to the right. Alright, excellent. Everyone seems to be getting that correct. That makes sense. Let's hit play. Yeah, it's moving at the same speed. Now, let's use an actual condition where you have friction. Yeah, I'm going to hit reset all. I'm going to reduce the friction. This is a bit too high. I'm going to move it somewhere over here, about 1/10 of the entire bar. Now, I'm going to drag the 50 kilo mass again. You can see that the slide has reappeared. Let me go ahead and click all the check boxes once again. This is extremely important, so that you know what's going on. Otherwise, you're just doing something qualitatively. But to be able to visualize things quantitatively, those all the data, you know, the mass and the speed, all that is quite helpful. Okay, I'm not going to press pause right now. Nothing happens because, well, There's no force applied, right? No external force, hence nothing should happen. This makes sense. Robot's not trying to push the mass, nothing's happening. Yeah? How do you know the value of speed? I don't know the value of speed. I just know it's increasing or it's decreasing, Arjun. It's just a speedometer. I don't care what the actual value is. That's not so important at this point. The point is to see whether it increases, decreases, or remains constant. To do the actual calculations, you can do that using the equation that we just discussed a couple of minutes back. Yeah, you guys know all those equations. So you can actually put that down, and depending on time, because we're not worried about that. We just want to discuss things in a way to get a feel of everything we've learned in theory. We want to see them in action. That's the idea. Notice that this dude's not pushing the box, hence the sum of forces is 0, and yeah, so there's no friction basically. Make sense? Okay, now if I increase the speed, not the speed, the force, I have not paused the simulation. Okay, I haven't paused the simulation. Notice that this is the exceptional case. In other cases I would pause. In this case I haven't paused the simulation. So I make the force to be 20 newtons and then I hit enter. As soon as I hit enter, you can see now a red bar in the opposite direction. Besides the orange bar that was always there, there's also a red bar. What is this? What is this red bar here? Okay, friction. What kind of friction? It says frictional force, but what is there? Remember, we've discussed two types of friction forces. What do you think this is? Think carefully. Don't guess this. I mean, yeah, there are two options. If you guess one and I give you that, yeah, right now static, exactly. Yeah, static, because, well, static means stationary, kinetic means in motion. So, pretty obvious that is static friction. Remember, static friction was pretty cool. It adjusted to the change in force. If I change the force, the static friction also will increase. Obviously, to a limit, but it will increase. Now, we can see that in action now. Notice that the net force is still 0. And hence, the speedometer doesn't change. So, there's no change in motion. Yeah, that's verified. Now, I'm going to increase this and make it something like 40 newtons. Yeah? Okay? Are you guys okay with that? I'm going to hit enter, okay? Just please pay attention to this. Everyone here? Okay, cool. So I'm going to hit enter now, and what happens? Look at that. It started moving a little bit. But what has also happened is the value, the red value has changed. It's not 20 anymore. Yeah, it's increased to a different value. It's 35 now. Does that make sense? A little bit, yes, no, maybe. Exactly. 35 is the limit of static friction, not of friction itself, but of static friction. Yeah, we are assuming that there is no kinetic friction, and that case, let's not talk about kinetic at this point. Let's just talk about, yeah, limiting friction is 35. Okay. Now I pause this and I increase the friction slider and I put it, say, somewhere in the middle. Okay? Yeah? It doesn't really work, does it? It gives me a weird value. Hold on. I'm just going to reset everything so that this error doesn't happen. Let me do that once again. I'm going to keep this here right in the middle. I'm putting this box here. Let me choose a bigger value now. I'm going to choose a value of, say, like 50 newtons. It's still balanced out. Why did that happen? Earlier it was just only 35 newtons. What happened now? Can you guys explain this? Exactly, I've increased the friction. Yeah, you notice that initially I reduced the friction to a value which was about 1/10 of the total value, but now it's the same. So now I have 50, make it 60, still balancing it out, make it 80, still balanced out. Exactly. More the amount of friction, basically the rougher the surface. Yeah, this uh, bluntly put, the more rough the surface is, the harder it is for you to push anything, which makes sense. So what we're going to do now is at some point it should be balanced out. I already know this value, so I am sort of cheating here. But at this point, it is completely balanced out. At a value of 125 Newton, I make it 126 Newtons, it's going to move very, very slowly. So slowly that you probably can't even see it. Okay, so we were right here. I said that I know that at 125 Newtons, it's exactly balanced out. Now when I increase the force to even just 1 Newton more, 1 Newton may not be noticeable. So I'm going to make it like 130 Newton. Yeah. As soon as I do that and I hit enter, notice that I haven't paused the simulation. Okay. It's going to move. Why? Because I've gone over that limiting friction value. Does this make sense to you guys? Okay, excellent. Let me use that same value of lower friction so that any change is more visible. If the value is so high, it doesn't suit our purposes of learning things easily. Yeah. So I'm just going to make it a smaller value, say something like, yeah, I've reduced the friction. And now what I'm going to do is I'm going to do that same thing. I want to make it about 50 Newtons and I'm going to hit enter. Okay. I haven't paused anything. It starts moving. Now I'm going to let it just move for some time, after which I'm going to pause. I'm going to remove the robot. Yeah, just hold on, let it get a decent speed so that things are visible. Okay, I'm going to pause the simulation. Notice that the force is in the right hand side, which is the orange thing, and the red sign is basically the friction, and the sum of forces is the green thing, which is what actually causes the acceleration. Is this clear to everybody? Yes? Arjun, the use of the things to the bottom right, those guys are just random weights. That's it. They just felt like they wanted to do a little bit more animation, so they have a kid wearing a PHET t-shirt, which is where this simulation is taken from. It's a pretty cool website. You guys should check it out. It's a free website. That's where we get this simulation from. Can you click on the present? Come on, Arjun Nair, let's get this done with, and then maybe if we have time, then we can play around a little bit. Yeah, you can click on the present. I think the deal with the present is that you don't know what mass it is. So it's an exercise for you to figure out by increasing the force, you can actually back calculate the mass. Yeah, does that make sense? That present is basically an unknown mass. So you apply some force and you can see the sum of forces being some value, and then you can back calculate the mass. That's the idea behind the present. Okay, yeah. So what I'm going to do now is I'm going to remove the dude. Yeah, I'm going to make the force 0 newtons. What do you think is going to happen now? I haven't hit enter yet. Oh, quick gun there. I have an answer already. Does everybody agree with Ashna and Arjun? Yeah? Okay, let's see if that makes sense. Arjun Nair has spotted my next question. What I was going to ask you is, does the mass not turn around and go backwards as in the previous case? But it seems like Arjun Nair already has it figured out. Do the rest of you think he's okay in saying that it will slow down and reach 0? Does everybody agree with that? Yep, that makes sense. Let's see. Let's see if that actually happens. It should, hopefully. Okay, you see the sum of forces. Yeah, just stops. Okay? Cool? Everyone comfortable with this? Okay, cool. That made sense to everybody, which is good. Let's use another simulation. Just give me a moment while I share this window with you. Give me a second. Okay, are you guys able to see a new window now where a guy is standing with his hands on his hips and it says force is introduction. That's the tab that is selected. Is everybody able to see these things? Okay, so on the right hand side you see something called the free body diagram. I'm going to click show over there. Does this seem familiar to you guys? Oops, hold on. Yeah. Does it seem familiar? Remember, we've done these things in class. Notice the point of this free body diagram. What about the acceleration lab? Hold on. Jacob, what are you talking about? We're going to do the. You can play around with it. You guys will have links to all these labs. We are trying and showing you the most we can using limited time constraints that we have. You're most welcome to check out the other labs. Just 1 second. I have a raised hand somewhere. Can you guys tell me what your question is right here? I'm not sure which one of you has raised your hand. So just can you go ahead and type here? I'm sorry I missed that earlier. Can you go ahead and shoot? Does anybody have a question? Okay, maybe it was something you guys asked earlier and I must have covered it up. Okay, back to the lab. Yeah, I'm not going to change to no friction. I'm going to keep it as wood because wood has friction. Ice, according to these guys, would have no friction. I also want to see the sum of forces. So I'm ticking that. I'm not changing anything else. Yeah. So basically, the right hand side had a free body diagram control, the display control, the starting position control. Yeah, this thing over here, the object position and all that. Hold on. Let's look at friction instead. That would be a lot more interesting instead of this. I just noticed that it doesn't allow me to select the value of friction, and I want that. I want to be able to select the value of friction. So let's use this tab instead. Okay. So in this second lab, we're going to focus on the second tab. Yeah, second lab, second tab. Easy to remember. Same boxes, just checking everything. I also have a force control here. And notice I also have a control on the static friction value and the kinetic friction value. You guys see that? Everyone is able to view this? Okay, excellent. I can also change gravity. I can go to the moon or to Jupiter. Not going to mess with that right now, but if you guys want, sure, go ahead. Why not? Yeah, when you want to play with these labs. I have a record and a playback button. I mean, a button that can play back the simulations, just like the motion lab. Won't be using those extensive features, but just telling you that you guys can if you want to later on. Make sure that all these settings are chosen before you start. Check that the static friction is 0.5. Check that kinetic friction is 0.3, which is what it is. I'm going to change the gravity to 10 meters per second square. That's what we're using for at this level. Yeah, at this level of the program, we don't mind the gravity being taken as 10 meters per second square. So that's fine. Notice that the crate is at rest. And observe the free body diagram of the crate. Yeah, it shows you gravitational force downwards. What is this gravitational force? What is the value of this gravitational force? You guys can use chat to just tell me. The chat box itself. Normal chat box. The one. Gravitation force. Okay. What? Okay. Let me rephrase. What is Fg? The weight of the crate. M into G. Okay. What is the mass? It's simply 100 kilos. Everyone sees that the object mass is not changed. It's set to 100 itself. Yeah. So therefore, Fg or the weight would simply be, as you guys have correctly said, M into G, which is 100 into 10, which makes it 1000 Newton. Make sense? Well, since there is no vertical motion, you can see that the yellow upward arrow. Could I please increase the font size? Hold on. Yeah, don't worry about that at this point. You don't need those values right now. Is it looking blurred out or something, Arjun? We're not going to change any of those values, so don't worry about it. I'm only going to change the force. You should be able to see that. Are you able to view the force value? That's the only thing that matters at this point. Yes? The applied force 0.00 Newton. Can you guys see that? Yeah, in your individual video window itself, you can zoom in. Just press Control and scroll. You can just do that. So we have figured out that, yeah, as I was telling you guys, that you guys just need to be able to view the applied force thing there. Yeah, everyone can view that clearly. Don't worry about the other values. We're not going to change anything else. We're only going to change that and also the object position. Those are the only thing we will change. Okay, cool. So can you guys now calculate the maximum force of static friction? Given that static friction value is 0.5, mu s is 0.5 is given to you guys, and you guys know that the total force is 1000 newtons. And okay, I see an answer right away. Although an important thing that you guys need to know, which is quite trivial, but just to make it explicitly clear, since there is no vertical motion, the yellow bar, which is the normal force because of the earth or the wood floor that's on the crate, balances out the weight. Is everybody comfortable with that idea? Which is how you get that the normal force is equal to 1000 newtons, and hence static friction, as you guys have correctly calculated, is simply 0.5 into 1000, which is 500 newtons. Cool, excellent. What do you think the FBD is going to be like when I add a force of 100 newton? What will be the force of static friction if I apply a force of 100 newton? What do you guys think? Okay, Arjun Nair says it won't move. What about the force of static friction? What do you guys think about that? What's going to happen to that? Any ideas? There's some confusion about that. Let's see what happens. Again, I'm not hitting the play pause button. I'm just going to apply a force of 100 newtons. It will reduce. Okay, that makes sense. Notice that the arrows balance themselves out. Yeah, a very tiny force of 100 newton towards the right, and the same length orange bar is there towards the left. So as you guys have figured out correctly, most of you guys figured this out correctly, the limiting value is 500 newtons. Is that clear, Arjun Nair? And also the rest of you, if you had any doubt. The limiting force is 500, but the static force is a variable force, and it will be equal to the applied force until that value of 500 newton is reached. Does that make sense to everybody? Yeah? So now if I hit play, it's not going to move. Which is what happens. You see that it's going on, recording, etc., but nothing's happening. Cool. Make sense? Okay, great. Now I'm just going to hit clear, which is going to clear this force, and I'm sorry, which clears out the whole recording thing. Let's verify if the force of static friction is actually going to be variable. I'm going to enter speed force of 200 newton. I'm going to hit enter. You can see that both the yellowish force, exactly, it's 200 newtons. They have the same magnitude. You guys are able to see that, right? It increased. The orange bar, the orange arrow actually also increased along with this. Make it 300 newton. Same thing should happen. Make it 400 newton. Exactly, at 501 it begins to move, right? So up till this point it's the same. At 500 also it does not move. Now I'm going to make the speed a ridiculous value. I'm going to, not speed, why do I keep saying speed? I mean the applied force. I'm going to make the applied force something like 600 newtons. Clearly then force of will be greater, the force applied, which is FA should be greater than FF now. Does that make sense? You can actually see that in the arrow itself. The arrow is slightly longer. What will be the acceleration of the crate? Is there a way to calculate the acceleration? Yes? Exactly. What Arjun Nair said. You can also see that by this small green thing that says F sum. There's a small green arrow towards the right now. Everybody able to see that? Okay, excellent. What will the actual acceleration be now? If the net force is 100 newtons towards the right, what is the acceleration? You guys have the mass. It will be simply 100 by 100. Exactly, 1 meter per second square. Makes sense. Excellent. Now, the wall on the right is how far away? It's something like 14 meters away, right? 16 meters. Okay, let's see. I think it's 14. I'll just change the direction to give you a nice even number. Let's say I make the position something like, wait a minute, minus 8 meters. Okay. Now if I made the position minus 8 meters, the wall is exactly 18 meters away. Okay. How? 10 plus this minus 8. Yeah, exactly. Now 18 meters away. According to this equation that we have of distance, that s is equal to ut plus half at square, and obviously there's no initial velocity, so all that's left over is simply s equal to half at square. Is that okay? Are you guys comfortable with that fact? I can use the equation as just s equal to half at square. So according to this, if I have an acceleration of 1 and the distance is say 18 meters, how much time would it take, you think? 18 into 2 is 36. And what is root of 36? Simply 6 seconds. Arjun is giving me a different answer. Is that because of a mathematical error? That's because of mathematical error. Okay, cool. So it's 6 seconds. Okay, let's see. Let's see if that happens. So according to everybody, it should be about 6 seconds, right? Let's start counting, okay? When I say 3, 2, 1, go, start counting on your fingers if it actually takes 6 seconds. Okay? 3, 2, 1, go. Oh, that was a lot quicker than 6 seconds, wasn't it? Yes? What happened there? Yeah. Arjun Nair thinks it's, yeah, even I counted about a little more than 3, something between 3 and 4. Did everybody get that? It was clearly not, it was not 6, it was definitely not 6. Yeah? Why? What happened there? Did friction cease to exist? What do you think happened there? Any ideas? Maybe we got the wrong distance. No, the distance fine. You see the object position, you can see the sliders totally, you see that, right? Friction reduced. That's the only thing that could have happened. Remember, kinetic friction value is different from static friction. You guys remember that? Well, physically also, when you try and push a box, you're pushing it really hard and suddenly it starts moving and you get a jerk, right? That's basically because kinetic friction is always, well, I'm not going to say always because somebody is going to come up and say, hey, you know what, we figured out a way to make it higher. But usually kinetic friction is lower than static friction. And that's the value we have also chosen. In this simulation, we have chosen the kinetic friction to be 0.3. Correct? Yes? Does everybody agree with me? Agree with the reasoning behind why the time was so much lesser than just 6 seconds? Let's try and calculate that. What would be the frictional force when, yeah, Ashna, sure. Does everybody agree with me when I say that the coefficient of kinetic friction comes into picture when the body starts moving, and hence, as soon as the body starts moving, I need to choose a different value of FF, yeah, which is the force of friction. It would still be mu times n, it's just that mu changes. Yeah. So now the actual force of kinetic due to kinetic friction would be normal force, which is 1000, into mu k, which is 0.3. So the total force is 300 newtons. Does that make sense to everybody? Notice what happens. Now notice another thing. Look at the red bar. Keep looking at the red bar. When I'm going to hit play when I'm going to say 3 to 1, I'm going to hit play. Look at the red bar. Keep looking at the red bar, okay? You guys know what I'm talking about, right? When I say red bar, the FF in this F something. You guys see that? The top, the free body diagram. That's what I'm talking about. Okay. 3, 2, 1, go. Saw that? It's suddenly reduced. Exactly. That's the idea. That's what I was telling you guys. Now, that also rational. Now the acceleration also should change. What is the acceleration now? It's simply 300 now. 300 newtons divided by 100. Exactly. 3 meter per second square. Excellent. 3 or 2. Is it 3 or 2? It's 3, right? Yeah. Okay. Now solve this for the new acceleration and you put it back into that equation. S equal to half AT square. So you get a funny root. You get a, what do you get? You get 2 into 18, 36 by 3. You get root 12. Right? You get root 12. So root 12 is approximately 3.5 or 3.45 to be exact. That's the actual time it took. Yeah, you guys counted 2 root 3. Yeah, basically around 3.5 approximately. So, does everybody agree with me? The reasoning behind why it took lesser than 4 seconds when we actually hit the play button. Okay, cool. So, that was a brief idea behind all of this business to do with friction, and basically today we built up the different ideas, the Newton's first law. We also spoke about the second law and also the third law. How? First law will obviously was where in the first lab, yeah, when we said that forces would actually you need an external force to first of all cause motion, and it stays, a body stays in the motion of rest or motion unless you had that external force. The second law, force is simply equal to mass times acceleration. Yeah, it kept going exactly, which is what you've used throughout to figure out this acceleration value. Friction reduced because friction changed at different places. Friction reduced because when a body starts moving, kinetic friction takes over. Until the body starts moving, until it has a tendency to move, the variable force, which is static friction, is there. Till what point? Till the limiting value. Exactly. As soon as we overcame the limit, the friction reduced and it became kinetic friction. I know that sounds crazy, but nature's pretty cool. It does these things. Yeah? Okay. So back to the, yeah, exactly, Arjun Nair, correct. So back to the recap idea that I was going through. The third law was explained because of this idea of friction, yeah? First of all, you find a normal force. In this case, it happens to be equal to the weight. I've kept saying again and again, it's not necessarily true. Keep that in mind. Only because there is no vertical motion, you have this, the normal force to be equal to the weight. Okay, I'm going to pause this lab thing and we'll get back to class, okay? I'm going to pause this lab session.